Welcome everyone to this explainer. Step right up to the high-stakes table. Think of your Cambridge computer science exams, whether you're sitting the 0417, 0478, 2210, or 9618 syllabus, like a high-stakes game. The examiner is the house, and the house always has a system. But today, we're going to learn how to play the examiner's game and win big. You have to know exactly when to hold, when to fold, and when to go all in. I want you to imagine two classic students. We'll call them Alex and Sam. Now, Alex is the kind of student who overloads every single answer with raw, unfiltered computer science facts, but zero actual analysis. And Sam rushes. Sam completely misses the command word requirements and leaves incredibly easy marks on the table. Throughout this explainer, we are going to look at their flawed answers, covered in red pen marks, and compare them to the top-tier strategies you need to be using. We're talking about the Data Representation Exam Mastery Playbook. We are going to look at the exact differences between high-scoring answers and low-scoring answers, straight from the teacher's comments. So get ready, let's dive right into this.
Here is our roadmap for today's session. We have 5 crucial steps to get through. Number 1, the binary foundation. Number 2, math, shifts, and logic. Number 3, digitizing real-world media. Number 4, shrinking data, file compression. And finally, number 5, exam mastery strategies.
Let's kick things off with Section 1, the binary foundation, understanding how absolutely every piece of data starts with simple ones and zeros.
Okay, let's talk about hexadecimal. While computers inherently run on binary, humans and programmers almost always use the hexadecimal system. Why is that? Well, because a massive long string of ones and zeros is incredibly hard for us to read, write, and debug without making mistakes. Hexadecimal, which is base 16, compresses that binary into a much more readable format using the numbers 0 through 9 and the letters A through F. Now here is where our student Alex usually goes wrong. When the exam asks for the uses of hexadecimal, Alex just writes, "It is used by programmers because it's easier to read." 0 marks. The examiners don't want a generic definition. They want specific real-world applications. If they ask for the uses of hexadecimal, you need to have these core examples locked and loaded. You need to mention error codes for memory locations. You need to explicitly state media access control or MAC addresses, which identify a physical device on a network. You should mention Internet Protocol or IP addresses, specifically IPv4 and IPv6. And finally, HTML color codes. For instance, using the hex code #FF0000 to tell a web browser to display pure red. Don't just give the theory, give the exact application. Lock these 4 uses in your memory right now.
Moving right along to Section 2, math, shifts, and logic. Because binary isn't just static data sitting in a hard drive, it is constantly being manipulated. And before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at how we actually calculate with binary.
Let's break down the mathematical logic of binary addition. It operates heavily on very specific carry and sum rules. It's actually quite simple once it clicks. 0 plus 0 is 0. 0 plus 1 is 1. But here is the kicker. When you hit 1 plus 1, the sum is 0, and you carry a 1 over to the next column. It's exactly like base 10 addition when you hit 10, but here it happens at the number 2. Now, when you're structuring your answers, I want you to think about the Peel framework. Point, evidence, explanation, link. Make your point clear, show the evidence through your mathematical working, explain the carry logic, and link it back to the final 8-bit number. If you are faced with a binary addition question, you must always clearly show your carry values in a separate row above or below your answer. That is your evidence.
And showing your work leads us perfectly to a classic exam trap, the overflow error. Listen, an overflow error occurs when the result of a calculation is simply too large for the allocated word size. This is where our other student, Sam, loses marks. Sam rushes. Sam adds up the numbers in his head, writes down an answer, and completely ignores the physical limitations of the computer's memory. The crucial point is this. If you add 2 8-bit numbers together, the absolute maximum value an 8-bit register can hold is 255. If your binary addition generates a 9th bit, a carry bit that gets pushed up the edge, it literally cannot be stored in that 8-bit register. The computer will essentially drop it, resulting in a wildly incorrect number. Examiners absolutely love to give you an addition problem that purposely overflows, just to see if you are paying attention. They want to see if you will catch that hidden 9th bit and correctly identify the overflow error, instead of just blindly writing down the remaining 8 bits. Next up, let's tackle negative numbers. How do computers handle a minus sign when all they understand is positive voltage and zero voltage? They use something called 2's complement notation, where the leftmost bit represents a negative value, like minus 128. Converting a negative denary number into binary can seem daunting, but I am going to give you a foolproof 3-step procedure. If you follow this, you will completely eliminate careless errors. Step 1. Simply write out the positive binary value of the number. Step 2. Flip all the bits. Invert every single 1 to a 0 and every single 0 to a 1. Step 3. Take that inverted result and simply add 1 to it using the binary addition rules we just talked about. That's it. If you use this exact 3-step method on your exam paper and physically write out each step, you will beat the examiner at their own game every single time.
Now, let's look at the literal transformation from a failing grade to a top-tier grade. This brilliantly illustrates why formatting matters. Let's compare a high-level exam answer to a low-level exam answer. The high-level student didn't just write a string of numbers. They drew out a full 8-bit register table, putting 128, 64, 32, 16, 8, 4, 2, and 1 at the top of the columns, and placed their numbers cleanly inside. When they had to perform a logical shift, they could literally just visually move the numbers left or right across those columns. It's foolproof. But look at the low-level answer. This is Sam again, rushing through the paper. Sam did the math in his head, but when he wrote the remainders, he wrote them from top to bottom instead of bottom to top. Even worse, he completely failed to infill the extra zeros on the left side to make it a proper 8-bit format. Those are incredibly easy marks, just thrown out the window because of a lack of structure.
I want you to really absorb this next point. I'm going to read you a quote straight from the teacher's grading comments. Where a mathematical sequence of operations is needed, it is imperative that you show all your working so that some marks can still be gained even if your answer is incorrect. Think about that. This is your golden rule. This is your insurance policy. If you just write down the final 8-bit answer and you made one tiny mental math mistake, you get a 0. But if you draw the grid, if you show the carry values, and if you draw arrows indicating the shifts, the examiner will look at your process. They will say, okay, they made a tiny addition error, but they understand the logic of a left shift, and they will give you partial follow-through marks. Never leave the house without showing your work. All right, let's move into Section 3, digitizing real-world media. We are taking those abstract numbers and translating them into reality.
Sound in the real world is an analog wave. It's continuous. But computers are digital. They only understand discrete blocks of data. So we have to chop that sound wave up into digital slices to store it. There are 2 critical definitions you must memorize and do not get them confused. First, sampling resolution. This is the number of bits per sample used to represent the amplitude or the loudness of a sound. Second, sampling rate. This is how many of those individual sound samples are taken every single second. Think of it like a grid. The sampling rate is how many slices you take left to right over time. The sampling resolution is how many increments of height you have to measure the volume from top to bottom.
Let's look at the visual proof of this so it really locks into your brain. Picture a graph. If we use an 8-bit sampling resolution, the computer only has a small range of numerical values to represent the amplitude. So when it tries to trace a smooth analog sound wave, it has to round the values up or down. The resulting digital curve looks like a jagged staircase. It's wildly inaccurate. But if we increase that to a 16-bit resolution, suddenly we have thousands of more distinct values to represent that amplitude. The digital points can hug that analog sound wave much more tightly. The staircase becomes so incredibly fine that it starts to look like a smooth line. Increasing the sampling resolution directly and dramatically improves digital audio accuracy. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acedexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, a very similar concept applies to visual media. You need to know the difference between color depth and image resolution. Color depth is the number of bits used to represent each possible color in a single pixel. If you have a color depth of just 1 bit, your options are literally 0 or 1, black or white. If you have a color depth of 32 bits, you get millions upon millions of precise color gradients. Image resolution, on the other hand, refers to the total physical number of pixels that make up the entire image, the width multiplied by the height. You must remember these 2 specific definitions because they are the exact variables we are going to need to calculate file size in our next section.
Which brings us to Section 4, Shrinking Data, File Compression.
This is where the math gets real. We are entering the interactive workshop phase of this explainer. On your exam, you will almost certainly face a data scan challenge where you are asked to calculate file size. So let's run through the speed writing method. Step 1. You take the image resolution, meaning the total number of pixels, say 1920 by 1080, and multiply it by the color depth in bits. This gives you the massive total file size in bits. But the examiner isn't going to let you stop there. They will usually ask for the answer in bytes or kibibytes or megabytes. So step 2, divide your total bits by 8 to convert them into bytes. Step 3, divide by 1024 to get kibibytes, and divide by 1024 again to get megabytes. Here is the ultimate trap. Always double-check the specific unit the command word in the question is asking for. If they ask for megabytes and you leave it in kibibytes, you lose the final mark.
Now, because these high-resolution files are so massive, we have to shrink them using compression algorithms. The syllabus requires you to deeply understand the difference between lossy and lossless compression. Let's apply our PEL framework here. If the examiner asks you to evaluate lossy compression, your point is that it permanently eliminates unnecessary data. Your evidence is that the original file can never be perfectly reconstructed. Your explanation is that we use this for MP3 audio and JPEG images, stripping out sound frequencies or slight color variations where human eyes and ears simply won't notice the missing data. The link is that this results in a massively smaller file size for fast streaming. Lossless compression, on the other hand, means absolutely no data is lost. The original file can be perfectly reconstructed bit for bit. We use this for text files, spreadsheets, or executable code, where losing a single character would completely ruin the file.
So how does lossless compression actually work without throwing anything away? One of the most common algorithms you need to master is run-length encoding, or RLE. I want you to visualize a matrix of pixels. Imagine a solid blue sky in a video game. Instead of recording the color data of every single individual pixel, saying blue, 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 blue 1,000 times over, which takes up a huge amount of storage space, RLE simply looks for repeating patterns. It scans the data, finds a streak, and records a multiplier. So instead of 1,000 individual blue records, it just records 1,000 blue. It's incredibly efficient for images with large areas of flat color.
And this exact same logic works brilliantly for text. Let's look at how RLE encodes text data. If we have a long string of the letter A repeating 8 times in a row, RLE shrinks this repeating data by turning it into a mathematical count. It generates a 3-byte sequence, 255, 08, 97. Now, what do those numbers mean? The 255 is a special flag. It tells the computer, hey, stop reading normally, a repeating sequence is coming. The 08 is the repetition count. It says the item repeats 8 times. And the 97? That is the standard ASCII decimal code for the lowercase letter a. So with just 3 numbers, it replaced 8 characters. It miraculously shrinks the data without losing a single drop of actual information.
We've reached Section 5, Exam Mastery Strategies. This is where we pull all of these concepts together to maximize your marks on exam day.
Let's look at another head-to-head comparison. This is a final set of sample answers focused on data compression. The high-level student, using that PEL framework we talked about, explains exactly what happens. They state that lossy algorithms eliminate data and the file is permanently unrecoverable, and then they link that to a massive reduction in size, allowing for faster network uploads and less bandwidth consumption. But look at our friend Alex's low-level exam answer. Alex just writes vague, unscientific phrases. He says lossless is more complicated and that compressing a file just uses up less space. It sounds like a casual conversation, not a computer science exam, and the examiner will punish that.
Let me show you exactly how brutal the marking scheme is. Read this teacher's comment regarding Alex's answer. The word space on its own is worth 0 marks. It needs to refer to storage space or memory space. Let that sink in. You could understand the entire complex logic of run-length encoding, but if you tell the examiner that compression saves space, they will ruthlessly tank your grade and give you 0 marks for that point. You aren't saving space. You are reducing the storage space or the memory space required. In computer science, precision is absolutely everything.
So let's summarize the core rules of our playbook, derived directly from our analysis today. Number 1, always draw the physical 8-bit register format, 128 down to 1, to prevent shifting and overflow errors. Number 2, show every single calculation step, including carry bits, to secure those vital partial follow-through marks. Number 3, use incredibly precise terminology. It's storage space, not just space. And number 4, if the command word in the exam asks you to comment on a logical shift or an addition, you must explicitly state what the expected mathematical result was in denare and clearly compare it to the actual result generated by the binary.
Data representation isn't just about mechanically memorizing binary and hex, it's about proving to the examiner that you understand the underlying logic of a computer system clearly, logically, and precisely. You know the strategies now. You know exactly what the examiners are looking for. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.